I want to start with a question that sounds like it should have a simple answer and does not. The question is, why does mass create gravity? You have heard the answer many times. Mass curves spacetime. Spacetime curvature causes objects to follow curved paths. We perceive those curved paths as gravitational attraction. The answer seems complete. But if you push on it, if you ask why mass curves spacetime, or what spacetime actually is, or why the specific relationship between energy, momentum, and curvature takes the form it does in Einstein's field equations, you quickly discover that the answer is much deeper and much stranger than the textbook summary suggests. And the deepest answer, the one that I think most physics education misses, is not merely technical. It changes the entire conceptual framework for thinking about gravity. It changes what gravity is. It changes what space-time is. And it connects mass to the structure of the universe in a way that is not at all obvious from the usual descriptions of curved rubber sheets and bowling balls. Let me start with what Newton said about gravity, because Newton's formulation, while incomplete, captures something that Einstein's formulation must also capture and adds a mystery that Einstein's formulation resolves. Newton's law of gravitation, published in the Principia in 1687, says that every object with mass attracts every other object with mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals g times m1 times m2 divided by r squared. The constant g, Newton's gravitational constant, quantifies the strength of the gravitational force. Newton's law was extraordinarily successful. It predicted the orbits of the planets to high precision. It explained the tides. It predicted the return of Halley's Comet. It enabled the prediction and discovery of Neptune from orbital irregularities in Uranus. Its success was so complete that for over 2 centuries it was considered the definitive description of gravity. But Newton was deeply troubled by one aspect of his own theory: action at a distance. How does the sun reach across 150 million kilometers of empty space and pull on the Earth? There is nothing between them. No medium, no contact, no mechanism. The force simply acts instantaneously at a distance. Newton himself wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He was troubled by his own theory. He knew it was incomplete. He could describe how gravity worked, but not why. The inverse square law was an empirical fact, not a derivation from deeper principles. The instantaneous action across empty space was a mystery he could not resolve. Einstein resolved it, but the resolution required rethinking the nature of space and time entirely. Einstein's resolution came in 2 steps. The first step was special relativity in 1905, which showed that there is no absolute space or absolute time, only space-time, and that the speed of light is the same for all observers. This immediately created a problem for Newtonian gravity. If the gravitational force acts instantaneously and there is no such thing as absolute simultaneity, then different observers would disagree about what instantaneous means, leading to inconsistencies. Gravity had to be a local phenomenon, propagating at most at the speed of light. The Newtonian instantaneous action at a distance was incompatible with special relativity. The second step was the equivalence principle, which Einstein called the happiest thought of his life, reportedly occurring to him in 1907 while he was sitting in his office at the Swiss Patent Office in Bern. The thought was this: a person falling freely cannot detect the effects of gravity in their immediate vicinity. A freely falling observer is locally equivalent to an observer in empty space far from any gravitational source. This is the equivalence principle. The local effects of gravity are equivalent to the local effects of acceleration. An observer in a closed box cannot distinguish whether they are at rest on Earth's surface, feeling the force of the floor pushing up on them, or accelerating upward in empty space with the same acceleration. The physics inside the box is identical in both cases. If this is already shifting your thinking about what gravity fundamentally is, the principles I have collected for understanding the fabric of reality address exactly this: how the deep structure of nature resolves apparent mysteries. Ready to change how you see the world? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. The equivalence principle has an immediate and profound implication. If gravity is locally equivalent to acceleration, and if acceleration is a statement about how space-time coordinates change, then gravity must be a statement about the geometry of space-time. Let me develop this argument more carefully. In special relativity, observers at different velocities measure different times and distances, as I described in the time dilation and distance videos. This frame dependence of measurements is governed by the Lorentz transformation. Accelerating frames introduce additional complications. The coordinate system of an accelerating observer is not simply related to an inertial coordinate system by a Lorentz transformation. Accelerating observers have their own geometry, their own way of defining distance and time. The equivalence principle says that this geometry of accelerating observers is the same as the geometry of observers in a gravitational field. So the geometry of space-time, the way distances and times are measured, is not fixed but depends on the presence of mass and energy. Mass and energy curve space-time in the sense that they change the geometry of space and time measurements. This is the deep answer to why mass creates gravity. Mass curves space-time not because of some mysterious force that acts at a distance, but because mass is a form of energy. Energy is a source of space-time curvature according to the Einstein field equations, and space-time curvature changes the natural paths of objects through space and time. But what does it mean to say space-time is curved? This is where the explanation usually becomes vague and unsatisfying, with rubber sheet analogies that mislead more than they illuminate. I want to give you a more precise picture. Space-time is a four-dimensional differentiable manifold equipped with a metric tensor. The metric tensor is a mathematical object that assigns an invariant interval to every pair of infinitesimally separated events. In flat space-time, the metric is the Minkowski metric I described in the space-time interval video. ds squared equals minus c squared dt squared plus dx squared plus dy squared plus dz squared. In curved space-time, the metric is different. It has coefficients that vary from point to point, reflecting the local geometry. The metric tensor encodes all the geometric information about space-time: distances, angles, volumes, the rates at which clocks run, the curvature of space-time. Everything that can be locally measured is determined by the metric. The curvature of space-time is described by the Riemann curvature tensor, which is derived from the metric tensor and its derivatives. The Riemann tensor measures how parallel transport of vectors around small loops changes the vectors. In flat space, parallel transporting a vector around any closed loop brings it back unchanged. In curved space-time, it comes back rotated, and the degree of rotation is measured by the Riemann tensor. The Einstein field equations relate the Riemann curvature of space-time to the distribution of energy and momentum. G min u equals 8 pi g divided by c to the fourth times t min u. The left side, the Einstein tensor G min u, is a specific combination of the Riemann curvature tensor and the metric. It encodes the curvature of space-time. The right side, the stress energy tensor T nu, encodes the distribution of energy, momentum, pressure, and stress. in the space-time. The constant of proportionality, 8 pi g over c to the fourth, sets the scale. It tells you how much curvature one unit of energy, momentum, density creates. The field equations are a set of 10 nonlinear partial differential equations. They are extraordinarily difficult to solve in general. The few known exact solutions, including the Schwarzschild solution outside a spherical mass, the Kerr solution outside a rotating mass, and the FLRW solution for a homogeneous expanding universe, were found under specific symmetry conditions that simplify the equations. Let me describe what each side of the field equations means in physical terms, because the abstract tensor notation can obscure the physical content. The right side, the stress energy tensor T manu, is a 4x4 matrix of numbers at each point in spacetime. Its components encode different aspects of the distribution of energy and momentum. T, 0, is the energy density, the energy per unit volume at each point. For ordinary matter at rest, this is rho times c squared, where rho is the mass density. T, 0I, where I runs from 1 to 3, is the momentum density in the ith direction, the energy flux or momentum per unit volume. T, ij, where I and j run from 1 to 3, is the stress tensor. T, 11 is the pressure in the x direction, T, 22 in the y direction, T, 33 in the z direction. T, 12, T, 13, T, 23 are the shear stresses. For a perfect fluid at rest, the stress energy tensor is diagonal. T0 equals rho c squared, T11 equals T, 22 equals T, 33 equals P, where P is the pressure and all off-diagonal components are 0. This is the form appropriate for matter and stars, cosmological fluids, and most astrophysical applications. The left side, the Einstein tensor G, nu, is built from the Riemann curvature tensor R, nu rho sigma, which measures the intrinsic curvature of spacetime. The Einstein tensor is specifically the trace-reversed Ricci tensor. G mni u equals R mni u minus 1/2 times G mni u times R, where R nu is the Ricci tensor, obtained from the Riemann tensor by contraction, and R is the Ricci scalar, the trace of the Ricci tensor. The Einstein tensor has the crucial property that its divergence is automatically 0. The covariant divergence of G mini u equals 0, identically as a consequence of the Bianchi identity for the Riemann tensor. This is physically important because the divergence of G mini u is 0 and G mini u is proportional to T mini u. The divergence of T mini u is also 0. The vanishing divergence of T mini u is the covariant conservation of energy and momentum. The Einstein equations automatically enforce energy momentum conservation. This is one of the most beautiful features of general relativity. The geometry of space-time automatically enforces the conservation of energy and momentum of the matter within it. The conservation laws are not imposed separately. They emerge from the geometric identity. The constant of proportionality, 8 pi g over c to the fourth, has a specific value because of how g, c, and the conventions of the metric are defined. In the Newtonian limit, the field equations must reduce to Newton's law of gravity, and this requirement fixes the coefficient to be exactly 8 pi g over c to the fourth. The factor of 8 pi comes from the spherical geometry of the Newtonian gravitational potential. It is related to the solid angle of a sphere, 4 pi, and the specific way the Ricci scalar relates to the gravitational potential in the weak field limit. The field equations encode the statement that energy and momentum curve spacetime, mass is one form of energy, through E equals mc squared. A massive object has energy density proportional to its mass density times c squared. This energy density appears in temnu and curves the space-time geometry described by gmu. But the field equations also say that pressure, momentum flux, and shear stress curve space-time, not just mass. Every form of energy and every flow of momentum contributes to the curvature of space-time. A room full of hot gas curves space-time more than the same room at absolute zero, even if the mass is the same, because the thermal energy and the pressure of the gas contribute to Tmu. This is one of the most important and least discussed aspects of general relativity. Gravity is not a force between masses. Gravity is the curvature of space-time caused by all forms of energy and momentum, of which mass energy is only one contribution. What we have just discovered is one of the deepest principles in all of science, that energy, not just mass, curves space-time, that gravity is geometry, that the laws of nature are built on a structure far more unified than it appears on the surface. These are the kinds of insights that the 12 principles in my book help you see and remember. Get 12 principles for understanding the fabric of reality at realityprinciples.com. Now let me address the question of why objects fall, because this is where the geometry of space-time becomes most vivid and most counterintuitive. In Newtonian mechanics, objects fall because the gravitational force pulls them toward massive objects. The Earth exerts a force on a falling apple, and the apple accelerates downward. In general relativity, there is no gravitational force in the fundamental sense. Gravity is not a force. It is the curvature of space-time. Objects are not pulled toward each other. They follow the straightest possible paths through curved space-time. The straightest possible path through a curved space is called a geodesic. In flat Euclidean space, the straightest path between 2 points is a straight line. On the curved surface of a sphere, the straightest path between 2 points is a great circle. On the surface of a sphere, great circles are straight in the sense of being locally straight. At any point on a great circle, the path does not turn left or right. But globally, great circles curve around the sphere. The same principle applies to space-time. A geodesic in space-time is the path that is locally straight, meaning it does not accelerate in any local inertial frame. A freely falling object is on a geodesic. At every point along its path, there is a local inertial frame, the freely falling frame in which the object is momentarily at rest or moving at constant velocity, experiencing no forces. The geodesic equation in general relativity is d squared x to the mu over d tau squared plus gamma to the mu sub rho sigma times dx to the rho over d tau times dx to the sigma over d tau equals 0. The symbols gamma are the Christoffel symbols, which encode the rate at which the coordinate basis vectors change from point to point. They are derived from the metric tensor and its first derivatives. In flat space-time, the Christoffel symbols are 0 in Cartesian coordinates, and the geodesic equation reduces to d squared x over d tau squared equals 0. Straight line motion at constant velocity. This is Newton's first law. In curved space-time near a massive object, the Christoffel symbols are non-zero. The geodesic equation picks up terms that, in the Newtonian limit of slow velocities and weak fields, reduce to d squared r over dt squared equals minus gm over r squared, Newton's inverse square law. The geodesic equation in curved spacetime produces Newtonian gravity as an approximation. Let me make the most important conceptual point explicit. A freely falling apple is following a geodesic through curved spacetime. It is, in the most fundamental sense, not accelerating. It is moving as straight as it can through the curved geometry. The curvature of its spatial path, which looks like it is accelerating downward under a gravitational force, is a consequence of the curvature of space-time, not of a force. You standing on the surface of Earth are not on a geodesic. The ground is pushing you off your geodesic with an upward force. You are accelerating upward at approximately 9.8 meters per second squared, which is why you feel your weight pressing you into your feet. If the ground were removed and you fell freely, you would be back on your geodesic and would feel weightless. This is the essential insight of the equivalence principle. The freely falling frame is the inertial frame. The frame standing on Earth's surface with the ground pushing up is the accelerating frame. The direction of the logic is exactly opposite to the Newtonian picture. In Newton, the natural state of an object is rest in absolute space, and forces accelerate objects away from rest. In Einstein, the natural state of an object is free fall along a geodesic, and forces push objects off geodesics. Standing on the ground is not the natural state. It is an accelerated state, with the ground imposing a continuous upward force. The curvature of space-time near Earth is what causes the geodesics near Earth to be curved paths that spiral toward the Earth. In the absence of the ground, you would follow a geodesic, a curved path in space-time that corresponds for short times to falling downward in space. The ground prevents you from following your geodesic by exerting an upward force. Now let me address the deepest question I can raise about why mass creates gravity. The Einstein field equations can be derived in several ways. But before discussing that derivation, let me describe gravitational waves, because they are the most dramatic confirmation that space-time curvature is real and dynamic. If space-time is curved by energy and momentum, and if energy and momentum can change over time as objects move and accelerate, then the curvature of space-time must also change over time. Changing curvature propagates through space-time as waves, gravitational waves. Einstein predicted them in 1916, a year after publishing general relativity. The strain produced by astrophysical sources, even violent ones, is extraordinarily small when it reaches Earth. The first detected gravitational wave from the merger of two black holes approximately 3 billion light years away had a strain of approximately 10 to the minus 21 at Earth. This means the wave distorted space by 10 to the minus 21 of any given distance, which for a 4-kilometer baseline is approximately 10 to the minus 18 meters, 1,000th the diameter of a proton. Detecting this distortion required LIGO, the Laser Interferometer Gravitational Wave Observatory. On the 14th of September 2015, both LIGO detectors simultaneously recorded the characteristic chirp of increasing frequency and amplitude from the in-spiral and merger of two black holes of approximately 36 and 29 solar masses at 1.3 billion light years. The missing approximately 3 solar masses were converted to gravitational wave energy in approximately 0.2 seconds. Kip Thorne, Rainer Weiss, and Barry Barish received the Nobel Prize in Physics in 2017 for this detection. Each gravitational wave detection is a direct measurement of space-time curvature changing over time. The mass and motion of merging black holes distort space-time, and that distortion propagates at c. This is why Newton's instantaneous action at a distance was wrong. Gravity propagates at c as a wave of space-time curvature, not instantaneously. Einstein resolved Newton's deepest worry. One derivation of the Einstein field equations starts from the action principle. The Einstein-Hilbert action is S equals the integral of the Ricci scalar r, which is the simplest curvature invariant, times the square root of the determinant of the metric over space-time volume. Varying this action with respect to the metric gives the Einstein field equations in vacuum. Adding the matter action gives the full Einstein field equations, including the stress energy tensor. The specific form of the action, with the Ricci scalar as the integrand, is the simplest possible action that is diffeomorphism invariant, meaning invariant under arbitrary smooth coordinate transformations. And that gives second-order differential equations for the metric. This is the Lovelock theorem. In 4 space-time dimensions, the only diffeomorphism invariant gravity theory with second-order field equations is general relativity. This derivation shows that general relativity is, in a sense, the simplest possible theory of gravity, consistent with the requirements of diffeomorphism, invariance, and second-order equations. But it does not explain why the universe has these properties. Why does space-time exist? Why is it a 4-dimensional pseudo-Riemannian manifold? Why does it obey diffeomorphism invariance? These are questions that physics cannot currently answer. The equivalence principle itself, the deep starting point of general relativity, is not derived from more fundamental physics. It is an observed fact, confirmed to extraordinary precision. The Eötvös experiment, performed by Laurent Eötvös in Hungary in the 1880s and 1890s, and subsequently improved to astonishing precision, measured whether different materials fall at the same rate in the gravitational field. The modern version of the Eötvös experiment, using rotating torsion balances, has confirmed the equivalence principle to 1 part in 10 to the 13th. But this experimental confirmation is not an explanation. We do not know why the gravitational mass, which determines how strongly a body is attracted by gravity, equals the inertial mass, which determines how strongly a body resists acceleration. We just observe that they are equal. And Einstein built his theory on this equality. The deep reason why mass creates gravity at the most fundamental level is we do not fully know. We know the how with extraordinary precision. The Einstein field equations correctly predict gravitational phenomena from stellar orbits to gravitational waves to the expansion of the universe. But the why, the reason that the energy momentum tensor sources space-time curvature with the specific coefficient 8 pi g over c to the 4th, is not derived from a deeper principle. It is the observed relationship encoded in the field equations. This is not a failure of physics. It is a frontier. General relativity may be a low-energy effective theory of a deeper quantum gravity. In string theory, gravity emerges from the dynamics of closed strings, and the specific form of the Einstein equations emerges as the massless spin, 2 closed string mode becoming the graviton. In loop quantum gravity, the geometry of space-time is quantized, and the Einstein equations emerge from the dynamics of the spin network. In the ADS CFT correspondence, the bulk space-time geometry, including gravity, emerges from the entanglement structure of the boundary quantum field theory. The question of why mass creates gravity leads us to the very edge of what physics currently knows. This is one of the most exciting places in all of science, where a well-confirmed theory meets its own limits and points beyond itself. The principles that help navigate this edge, that distinguish what we know from what we are still discovering, are in my book, Ready to Change How You See the World? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me describe one more aspect of why mass creates gravity that I think is underappreciated: the role of energy rather than mass as the source of curvature. In Newtonian gravity, only mass creates gravity. 2 identical objects at different temperatures produce exactly the same gravitational field because they have the same mass. In general relativity, this is not true. The hotter object has more energy, and the additional thermal energy contributes to the stress energy tensor, creating additional space-time curvature. The difference is tiny for any object we can create in the laboratory, but it is real and calculable. More dramatically, a region of space with a high density of electromagnetic radiation with no matter present curves space-time. Pure light has no mass, but it has energy, and energy curves space-time. In the early universe, The energy density was dominated by radiation, and the gravitational effects of that radiation drove the early expansion and deceleration of the universe. Even more dramatically, pressure curves spacetime. The pressure in the core of a neutron star contributes significantly to the gravitational field beyond the contribution from mass. For a sufficiently massive neutron star, the pressure is large enough that the total gravitational field, including the pressure contribution, overwhelms the repulsive quantum pressure from neutron degeneracy, causing the star to collapse into a black hole. This is the Tolman-Oppenheimer-Volkoff limit, the maximum mass of a neutron star, and the pressure contribution to the gravitational field is crucial for its derivation. And most profoundly, the cosmological constant, or equivalently the energy density of the vacuum, curves spacetime and drives the accelerating expansion of the universe. The dark energy that dominates the current energy budget of the universe is a form of energy that has no mass. It is the vacuum energy, the energy of empty space. Yet it curves space-time and affects the global structure of the universe. This is the complete answer to why mass creates gravity. Mass is one form of energy, and energy in all its forms: mass energy, kinetic energy, thermal energy, radiation energy, pressure, and vacuum energy, sources the curvature of space-time through the Einstein field equations. The coupling between energy momentum and space-time curvature is what we call gravity. Mass is just the most familiar form of energy and the most dominant source of curvature in everyday situations. The deeper question, why does energy curve space-time at all, remains at the frontier. The equivalence principle is an observed fact. The field equations are the simplest diffeomorphism invariant field equations consistent with that fact. The quantitative strength of the coupling, Newton's constant G, is a measured parameter with no derivation from more fundamental theory. We know how mass creates gravity with extraordinary precision. We do not know why with the same certainty. Let me close with what I think is the most important conceptual shift that the correct understanding of gravity produces. In Newtonian physics, gravity is a force between objects. Objects have mass. Mass exerts force. Force accelerates objects. The mechanism is mysterious. The action at a distance is troubling, but the formalism works. In general relativity, gravity is not a force at all. It is the geometry of space-time. Objects with mass and energy curve the space-time around them. Other objects moving freely through that curved space-time follow geodesics. The geodesics in curved space-time look to observers tied to accelerated reference frames, like the paths of objects attracted by a force. But there is no force. There is only geometry. This is the real answer to why mass creates gravity. Not because mass exerts a mysterious force, but because mass is energy. And energy is the source of space-time curvature, and space-time curvature is what gravity is. The apple does not fall to the ground because the earth is pulling it. The apple falls because in the curved space-time near the earth, the geodesic through space-time that starts from the apple's initial position and velocity curves downward toward the earth. The earth is not pulling the apple. The earth is curving the space-time the apple is traveling through. The apple, following the straightest possible path through that curved space-time, falls. We started by asking why mass creates gravity and ended by discovering that gravity is not a force at all but a geometry, and that mass is just one source of that geometry among many. That kind of conceptual transformation, where a well-posed question leads to a completely different understanding of the concepts behind it, is what my book is built on. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What surprised you most in today's video? Tell me in the comments. If this changed how you think about gravity and its relationship to mass, if the idea that gravity is geometry rather than force looks different after understanding the Einstein field equations and the geodesic equation, tell me in the comments. Tell me whether you find the equivalence principle, the observation that all objects fall at the same rate, more or less miraculous after understanding that it is the observational foundation of general relativity. Tell me whether the contribution of pressure and radiation and vacuum energy to space-time curvature, not just mass, changes how you think about the relationship between gravity and the rest of physics. And subscribe if you want to keep going into the places where the most fundamental questions about the nature of space, time, and gravity meet the most precise physical theories ever constructed.